Good afternoon, everyone. Welcome to this session 5B, which is on AI for weather and climate, continuing on the talks that you heard earlier this afternoon. We have 5 speakers, and the first speaker would be getting 20 minutes for their talk, out of which 5 minutes we suggested is for Q&A. And all the other 4 speakers will get 15 minutes with 3 minutes for Q&A. I hope you'll make the session lively by hitting at provocative points so that there'll be interesting Q's and A's. And I will try my best to read them from the Slack. And of course, if we run out of time, then we'll have to just wait till we get the respondents, get the speakers to respond in offline in the Slack. Before I proceed, I think I just want to remind you of the code of conduct and etiquette that was drawn up and that's been circulated to all of you. So please adhere to it. That would be very much appreciated. So we are ready to hear, and the first speaker is William Chapman. The title of his talk is Forecasting Seasonal Western US Precipitation with Interpretable Machine Learning Trained on Large Climate Model Simulations. So William, go ahead.
All right, are you seeing my screen here?
Looks great.
Wonderful.
Yes.
Awesome. Well, thanks so much for coming out to this talk. Today, we'll be talking about training machine learning models on climate model output and show that it yields skillful, interpretable seasonal precipitation forecasts. So this is work that was led by Dr. Peter Gibson, who's now at NOAA, New Zealand. But he is super busy now, so I will be sharing it with you all. My name is Will Chapman. I'm a graduate student at the Scripps Institution of Oceanography, working for the Center of Western Weather and Water Extremes, and I'd like to acknowledge my co-authors listed here from NASA JPO and also from other members of the Center for Western Weather and Water Extremes. So this is a quick talk, and there's a lot of nitty-gritty detail in the paper and the project. So I want to point you first to the paper that just came out that sort of accompanies this talk, in Communications, Earth and Environment, of the same title. So if you are curious about some of the more minute details, please visit that paper link and check it out there. The big question that we're trying to answer with this talk is, can modern machine learning methods improve seasonal forecasting skills, specifically for West Coast precipitation? So really few studies have attempted these modern machine learning methods for subseasonal to seasonal or seasonal forecasting, mainly because these new machine learning methods are extremely data hungry and a barrier to utilizing machine learning. So in seasonal forecasting, we really get one new observation per year, and we only have so long of a historical record. Sort of to circumvent this problem, we propose to use to train various machine learning algorithms on large-scale climate model ensembles. So these ensembles span several thousands of years, and they're perturbed initial condition experiments, and they really provide unique opportunities to learn these predictability of the second kind, these boundary forcing signals within the model. So to be clear, we're not doing any sort of model post-processing here. These aren't forecasts, but we are taking large climate ensemble models and trying to forecast forward in time just based on those initial conditions. So typically, how do we do seasonal forecasting? Well, classically, we use these dynamic models, and this is a schematic from ECMWF showing how you do a disturbed initial condition, and you march these forward using the physics of the atmosphere and ocean in order to develop some sort of ensemble spread. You take a mean there, and then hopefully there's some signal outside of the noise that can give you some sort of prediction. And we've made giant strides in seasonal forecasting with dynamic models. However, in the NMME, which is a model that we are going to be comparing our machine learning forecasts to, we've seen that seasonal temperature forecast skill is shown to improve across successive model upgrades. However, minimum skill is found for precipitation, or at least minimal scale improvement. This suggests that potentially we're reaching some saturation point for the models run at this resolution, and we're going to need a lot more computational resources or increase our physics or improve our physics schemes. A lot is going to have to go into that. So we're hoping that potentially machine learning can kind of jump into this space and help to oyster the scale here. So really what we've done is we've developed a machine learning data set from NCAR's CSM, large ensemble model, the historical runs. The data set that we've made comprises of several thousands of years, and we take EOFs across known predictor variables for West Coast precipitation. These include tropical SSTs, tropical deep convection, and large-scale circulations. And these are all used as lagged predictor variables into the input of our machine learning methods. We then use these to predict the widespread seasonal. So we're looking at November, December, January, and January, February, March, spatial clusters of precipitation across the Western US. And I'll show you these clusters here in a second. So the machine learning approaches that we tested a suite of different machine learning algorithms, but these include some ensemble methods like random forests and gradient boosted decision trees, but also some deep learning stuff, multi-layer perceptrons and long short-term memory networks. I won't go into the exact architecture here, but all of that is contained within the paper. So after showing the machine learning tools only the climate model data, so we're training and we're validating on the climate model, we then take this offline and we apply the predictions to the historical observations by projecting those EOFs, grabbing the observational space and then making the predictions from them. And then we test on these hindcast predictions in the observational world. So to kind of show you the cartoon of all the machine learning space that we're sort of spanning in this project. So for machine learning processing, we're doing a lot of dimension reduction using PCA to grab the different EOFs and leading modes of variance in the atmosphere and ocean. We're then using some k-means clustering algorithms in order to then turn these into some categorical class that we are predicting for precipitation. And then for the ML for prediction, we're using random forests and these boosted ensemble methods, as well as long short-term memory networks that encode some sort of time derivative inside their neural network structure, as well as multi-layer perceptrons. So really we have multiple different machine learning methods that are tested. They all have unique advantages and disadvantages. And there's a hierarchy of complexity here that we found has added to the predictive skill of the overall method. So to get more specific of what predictor variables are actually going into this network, we're taking EOFs in different regions across the globe of SSTs, specifically looking at tropical Pacific SSTs, Western Pacific, Indian Ocean, North Pacific. And these have all been studied over years, over decades really, to show that they have some influence over North American precipitation. We're also grabbing deep convection anomalies from the tropics, specifically velocity potential at 200 hectopascals, to encode some sort of convergence or divergence that is known to drive these vorticity sourcings that can eventually teleconnect to the extratropics and mid-latitudes. And then we're also looking at the jet stream in the subtropics in the North Pacific, as well as different geopotential height anomalies in the Eastern Pacific. And just to show you what some of these patterns look like, if you take tropical Pacific SST, the leading mode is obviously ENSO. This is expressed in the La Nina state right now. But then you have these other driving modes that sort of modulate the variance on top of it. So for this, we're taking all these regions. So as a schematic for the workflow sort of our paper, we are taking EOFs in the regions defined above in both SST and in the atmosphere. These are then input into our machine learning algorithms. And what we're trying to do is predict the clusters of widespread precipitation here. These clusters were in EOFs as precipitation in North America and then running k-means clustering algorithms sitting on top of that. So anyone that is familiar with North American precipitation can pick out some of these patterns pretty easily. We see these classic north-south dipoles of precipitation characteristic of ENSO seasons. We also have a widespread wet conditions across the season and sort of a drought condition across the season. So the machine learning algorithms are trained on roughly 3,400 seasons, winter seasons from CSM lens. And then again, we're predicting NDJ and JFM. And so the skill is measured on these observational data sets. So really what we're doing is we're training in the model world, we're taking our little guy and we're moving over to the testing world. And what we want to do is compare our observations to the predicted space in the real world. So some classical statistical methods have been used in order to kind of try this problem in a statistical sense. Specifically, you can think of canonical correlation analysis or some multilinear regression stuff. And the benefits of those, they're trained on the observations typically, which means that inherently the physics are correct. They are using the observations to predict observations. However, they have a very small sample size. And this makes model complexity difficult and also tends to be prone to overfitting if you have too complex a model. Plus, you're waiting a long time for new data. So for our method, we are able to use these nonlinear algorithms which encode some variable interaction, and we can train on a really large data set. And it is a short wait for new and better data. As soon as a new climate model comes out, we can take that data and encode it. The big downfall is that the physical teleconnections in any weather or climate model are imperfect and do contain biases, and we readily encode those biases. And we're hoping that the models are close enough such that we can still get skill in the real world. So moving on to some results. What I'm showing you here on the y-axis is the accuracy of our machine learning model, or a given method. On the x-axis is that method. Anything in white is from the NMME. Anything is in red is from our machine learning models, and anything in blue is an ensemble of either the NME or the machine learning methods. In black, we show a baseline of the occurrence of our most popular class. So we want to make sure that we're above just guessing the most popular class inside the cluster or inside the training data set or testing data set. And then in black, we are also showing sort of a random guess model, like how lucky could you potentially get if you randomly selected, given our class imbalance, given our class balance, what is the most skill that you could possibly achieve? So something you can see is the machine learning methods are easily competing with all the NME, better than some, and competing with most. When you ensemble, you can get pretty equal skill to this too. JFM is more skillful than NDJ, which we would figure since the ENSO teleconnection is more active in JFM than it is in NDJ. There's inherently more internal variability atmosphere in NDJ. So really the takeaway is the machine learning models can compete or outcompete many of the dynamic models for a much cheaper real-time cost. Something we found that was particularly interesting is the classification errors are not necessarily found to be random. So say rather than having a 4-class task, we decided to do a 2-class task. When the algorithm is missing, it tends to miss in a certain direction. So say you're a water manager and you wanted to know if Southern California was going to be wet or dry in this given season. If you combine class 1 and 2 and class 3 and 4 to see either dry conditions or wet conditions in the Southern California area, you can achieve skills of upwards of 75 to 80%. In JFM, we are not so skillful in NDJ, but still some promising science here by combining these classes. So now what I'm showing is a rock diagram. So we have true positivity rate of our algorithms on the y-axis and false positivity rate on the x-axis. So what you want is high true positives up here in the upper left corner. What you'd like is low false positives here on the left. So something that's immediately apparent is clusters 3 and 4 here, which are our dry patterns, are more predictable than clusters 1 and 2, which are the wet patterns. In fact, cluster 2 is never predicted. This is the widespread wet pattern. We're finding that it's particularly unpredictable and might be capturing a lot of the internal variability associated with these precipitation methods. So really one advantage of these clustering algorithms is we can also kind of look at what the predictable components of those back out the state of the atmosphere that sort of leads to that. So now moving into the more interpretable piece. I'm going to quickly buzz through this slide because anyone that has seen any of my recent machine learning tasks know that this is important. But you want to know what your algorithm is doing. So this is a fairly popular example in which they were trying to predict whether horses were in images. And what ended up happening is their network ended up picking up on the watermark of this photographer that liked to take horse pictures in order to make that prediction. So we wanted to make sure there was nothing like that going on. So the take-home message is we should really pay close attention to what it is that the machine learning algorithm has really learned. So I'm going to show you some of the methods that we broke down in the paper. I'm only going to be showing the ones on the random forests, but there's some other stuff contained within the paper. So what I'm showing here is variable importance within our random forest network. And in order to interpret this figure, what you want to look for is large dots that are low on the mean minimum tree depth, and the relative decrease in accuracy is high. So our most important predictive variables were shown in red here. As you would expect, the tropical Pacific SSTs with lags, especially EOF1, which is characteristic of the ENSO signal, is the most important variable. But what we also see is some importance of the lagged velocity potential variables, showing that there is some priming of the atmosphere prior to this, especially a few months before a peaking ENSO season, that could potentially be leading to more skill. Also, we see some Western Pacific SST modulation that seems to be important for modulating this forecast skill. Something that also shows up is that the North Pacific SSTs and the circulation are clearly not important. This is something you sort of expect given the internal variability in these the mid-latitudes, as well as the sort of memory of these signals. So moving on to something called partial dependence, and it's essentially showing the interaction between variables. So what these figures are showing us is that certain variables interacting with each other increase chances of clusters here. So to interpret this, essentially what this is saying is when SST of tropical precipitation, or the tropical SSTs are in a positive state, and the velocity potential is in a negative state, as given by these two patterns, we can have a more likely cluster for outcome. Showing that again, there's some priming of this atmosphere, especially at an early lag of the SST state. And then one last framework that we started to look at for interpretability methods is examining individual predictions and showing what was actually driving the network to either support or contradict a prediction. So for 2005, we correctly predicted this characteristic ENSO pattern. And what it's showing here is that largely this was looking at tropical SSTs, but there's also some look at some of the lagged velocity potential predictors that was kind of kicking towards this. So to wrap up, so we can get some questions here, in summary, training machine learning models on climate model simulations has been tested here, and we find the main advantage of this approach is that we can encode these nonlinear interactions between variables, and we also have this very long training data set. So the results show potential for such a seasonal prediction system trained in this way, and the machine learning does not really need to be considered a black box because we can really uncover how these predictions are made, and we in fact expect some further improvements with some recent testing that we're doing, specifically encoding some of the upper atmosphere and stratosphere QBO signals within our models. So with that, I'll throw the reference up here and take any questions that folks have.
Thank you very much, Will. That was a fascinating talk, especially pretty bold, going after these large ensembles and trying to draw the predictions from them. Just information to everyone, please put in your questions in the Slack. We already have one question, Will, for you. In this study, you're only looking at many ensemble members from one climate model. Do you anticipate the ML models would improve if training was done across different climate models?
Yeah, it's a really good question. It's a pretty big, heavy lift to incorporate more climate models, but we're currently in the process of grabbing more predictors from a suite of climate models. Results are still pending. I don't know if we squeeze as much skill out of these predictors as we have thus far, but I guess the answer is results are pending on that one.
I have a kind of questions on the back of that one. You spoke of the nonlinear interactions, and I'm just wondering, is the degree of nonlinearity in the system going to affect the outcomes from the ML-based simulations?
Yeah, it's a good question. To first order, you would think, ENSO, you get this precipitation signal. And so we need to do some more testing on exactly how much those nonlinear actions are actually in effect. What I can tell you is that we have done simple feed-forward networks in which we remove any of the nonlinear components from it, and we see a drop in skill. I can't tell you exactly what variables are interacting in what way because we haven't done a lot of tests in that, but we can see that there is some nonlinear component there that we are picking up on.
Okay, thank you. So I think we will, thank you, Will. We'll move on to the next presentation. And before I do that, I was remiss in not introducing myself. I'm Ramaswamy from NOAA's Geophysical Fluid Dynamics Laboratory. Very happy to chair this session. And so moving on to the next talk by Jason Stock. The title is Using Machine Learning to Improve Vertical Profiles of Temperature and Moisture for Severe Weather Forecasting. So, okay.
Oh. I should be sharing my screen. Can we all see it?
Yes.
Perfect.
You have to, yeah, that's right.
Looks
Looks
good.
good.
Sounds good. So thanks everybody for joining. My name is Jason Stock. I am a graduate student in the Department of Computer Science at Colorado State University. I also want to acknowledge the other collaborators I had on this work, specifically John Dandy, Emma Ebert-Uphoff, Jack Doslek, and Louis Grasso. They were all, especially Jack and Louis, the domain experts, were really helpful for this work. So deep convection, as many of us know, can occur anywhere in the United States or around the world. And the most severe events can be accompanied with threats to lives and properties. So, large hailstorms, tornado events, and so on and so forth. And this animation, while interesting, is just illustrating how quickly a storm can ignite over Oklahoma. So for meteorologists to forecast these events, having accurate boundary layer thermodynamic and kinematic profiles are of paramount importance. And traditionally, the radiosondes are the gold standard to actually provide these accurate representations for vertical profiles. The radiosondes themselves are launched regularly twice a day from different locations around the United States. And they're pretty spatially coarse, and they suffer from temporal paucity with being only launched twice a day. So it can be difficult to actually capture all the variability and changes in the atmosphere. So forecasters will instead use numerical weather prediction models or supplementary to radiosondes to forecast these convective threat assessments. But these NWP models are born, while they're born from lots of vast amounts of data and sophisticated physics, they include inherent errors that can really lead to the difference, say, in having a tornado event or having little convection risk whatsoever. So on the left here, we have a skew-T log P diagram showing the radiosonde, the RAOB, overlaid with the RAP, which is going to be the numerical weather prediction model. And I'll explain the data in a little bit more detail here in a minute, but it's just the two profiles overlaid on one another, and we can see that there's a noticeable difference. So the question here is, well, can we improve the vertical profiles of temperature and moisture in the NWP model using machine learning? So we propose using deep learning algorithms to combine NWP inputs as an initial guess, satellite data, and surface observations to produce retrievals of temperature and moisture that are closer to the actual radiosondes themselves. So in many ways, this is challenging because it's the first known work to actually do this with neural networks. And creating an algorithm that generalizes well is particularly difficult because the data is spatially and temporally sparse. We don't have as many samples as we would like, but that's common in a lot of atmospheric science applications. So the general overview of our model is using the numerical model as input, supplemented with the observational data, so analysis of surface observations, as well as satellite imagery from GOES ABI, into our machine learning algorithm, producing an estimate of the profiles, and then comparing that with the radiosonde. So we're producing estimates of the temperature and dew point. So for our ground truth, we're using radiosonde observations from the National Weather Service forecast office launches. And the model that we seek to improve is the rapid refresh model, which is a model that provides forecasters with situational awareness over North America. And then for satellite imagery, we're using GOES ABI, the water vapor bands, window channels, and then I'll kind of discuss how some of those channels are used. And then for surface observations, we're using an analysis from RTMA. So the data themselves are pre-processed and co-located on the radiosonde launch location and release time. The profiles from the numerical model and the radiosondes are linearly interpolated to 17 kilometers above the surface, which is the average geopotential height of the 100 millibar surface in the summer months over the US. And then GOES ABI radiances are converted to brightness temperatures. But we're focusing here, this is important, that we're focusing on 18 locations in the central United States. And this yields about 38,000 observations. So this diagram here we can see as input is going to be the RAP temperature, dew point, pressure, and geopotential height that's there on the left, along with the GOES channels and RTMA. We're only taking a patch from GOES, and this is the patch that's directly over the radiosonde launch location. And the same with RTMA. And then as output from our model, the target here is going to be the temperature and dew point that we hope is closer to the radiosonde observation. So we partition our data spatiotemporally with equal distributions. And what I mean by that is because we have soundings from different launch locations, we want to make sure that our training and validation and test sets have equal distribution of samples from each location and different times. For example, we don't want the test set to have all of the samples from Oklahoma and then the training set doesn't see that whatsoever. And then because we have the additional observational data, we want to see how important those are. So we're running a sensitivity study by training models with just the RAP in RTMA, the RAP in GOES, and the RAP GOES in RTMA. And then we also assess the importance of different GOES channels individually. And then we also just want to double check that there's no bias of seasonality or cloud coverage in our experiments. And I'm not going to talk about this in this talk, but we also directly estimated radiosonde products like K/sin to see if we can directly improve those instead of improving the profile prior. But that's beyond this talk. So we look at a breadth of different network architectures, starting with the simplest, which is just a linear model, and then going up to a fully connected model, a convolutional model, and then this residual unit. I'm going to focus here on the residual units because it provided the best performance. But for all of these models, we perform an architecture and hyperparameter search and train hundreds of different combinations, with each model being trained 5 different times with different initializations, and then computing means and standard errors, just so we can actually be sure of our results. So the residual unit, like I said, performed best. And here we have a diagram where we have, it's like a sequence to sequence problem where we have the RAP as input, and then we're trying to produce the radiosondes. And then in the bottleneck of the unit, we're actually inputting the GOES and RTMA data. So here are the general improvements. In these two figures, we have the temperature profile error on the left and the dew point profile errors on the right. The baseline, which is in this dark maroon, shows the root mean squared error between the RAP and the radiosondes without any model. This is just the error that already exists. So anything to the left of that is an improvement. So the yellow line is the RAP as input, and then the blue is RAP and GOES as input, and then RAP and RTMA, and then RAP GOES and RTMA. And what we can see is that we actually see a pretty good improvement. In this table, I'm not going to spend too much time, but it's just comparing the other models. So to look at the importance of different GOES channels, what we wanted to see is, well, we have these water vapor bands, we have these window channels. Are they actually providing information where we expect in the profiles? So on the left, we have a figure of the vertical weighting functions for the US standard atmosphere for the sensitivity of each band. We trained 3 individual models, one with all of the channels, one with just the water vapor bands, and then one with the without the water vapor bands. And what we see is that on the right figure here for the dew point, we actually see that the upper level moisture is improved better with the water vapor bands, kind of hinting that, yes, including these water vapor bands are doing what we would expect with improvements to the upper level moisture. Next, we look at cloud coverage. So the impact of cloud coverage, kind of trying to ask the question, are networks fitting the noise apparent in cloud samples, or are GOES ABI more useful in only clear sky conditions? And what we find is that when we train 2 different models, one only on clear sky and one on all of the data, we find that including the additional samples, even in cloudy conditions, is helpful for both the clear and cloudy conditions. So next, looking at is there any bias towards any particular time of year? And what we find is that for the most part, the results show a general improvement over all of the months of the year, but there are about 25% of the data that have errors larger than the baseline RAP, but they're not heavily influenced by the time of year. Similar with regional performance. Here we're just plotting on the bottom the root mean squared error change from the baseline to the machine learning estimates. So a brighter color or a greater percent change is a better improvement. And we find that without going into a whole lot of detail, just to, for time, in most scenarios, the networks favor the locations that have more samples or the greater number of, or the greater initial errors. So this suggests that locations that have more samples or have higher initial errors see the greatest improvements. So overall, we see with the unit a 26% reduction in errors over the baseline RAP profiles, with the greatest improvements in that mid to upper level moisture. And the GOES water vapor channels are critical here, and using both the clear and the cloudy sky samples are good. We do have some limitations. There's limited amounts of data, and improvements aren't uniformly seen across all of the samples. So some future work here is, well, why aren't there a uniform improvement across all the samples? So we're looking a little bit more at how we can interpret the networks, and how, looking at, is there any particular properties of the profile, say temperature inversions, that lead to these higher errors? And then also looking at different methods, like improving the loss function using CAPE or SIN, as opposed to something like a weighted mean squared error. So that kind of sums it up with the time given, but I'm happy to take any questions with time remaining. Thank you.
Thank you very much, Jason. That's very impressive. I don't see as yet any questions on Slack. Maybe I'll just ask the first question here. Given that, I think you mentioned at the outset of your talk that your focus is on severe weather, and then later on when you're talking about the different channels in GOES, with especially the weighting functions having peaks at different altitudes, I'm wondering whether there are some channels which are particularly important in terms of your ultimate goal. Is it the mid-troposphere or upper troposphere?
Yeah, that's a great question. I mean, so showing that the water vapor bands does have more information generally is kind of the observation that we did have, but perhaps looking at specific conditions where there are severe weather events and then seeing which channels help out the most or have the most attribution towards the model's estimate is something that we're planning to look at. So that's kind of scoped out for that future work, which is currently ongoing.
So I don't see any more questions. Oh, I do have one more question, which is, you're looking at radiosonde too, right? So the biases, in the sondes and GOES are obviously different. Do you pay attention to how to modify or correct for the fact that they have different kinds of biases?
If I understood that correctly, is that asking with the biases within GOES and the radiosondes?
Yeah, the biases in the measurements, in the values that you have.
Totally.
I mean, does it matter at all? That's the first part of the question. Does it matter at all? And if it does, do you make any attempts to somehow homogenize them or take them into account in some way?
Yeah, no, there's definitely some like internal variability or biases, especially with RTMA, where it's hard to see, like, is RTMA closer to, it's a surface analysis of surface observations, but is it closer to that of the radiosonde or the RAP? And what we see is that, yeah, there is this internal variability with a lot of the data, and like we can't necessarily smooth it out. We got to just treat the radiosondes as ground truth as they are. So there is going to be some bias with the radiosondes themselves. I think there's some work that you can do to kind of reduce some of the biases with the actual radiosonde, like the Weissla radiosonde measurements, but I'm not familiar with that right now.
Okay. And just a quick another question that came up on the Slack. Have you tried using data augmentation to increase sample size for training, especially for areas with low sample size?
Yeah, no, that's a really good question. Yes, initially, what we did was kind of perturb the RAP profile slightly. So you like kind of smooth it out or add kind of a sine wave to it to kind of bring in a little bit, like increase the differences at different altitudes. And it seemed that it didn't affect the results that much, unfortunately. But there could be ways in which we could use simulated data that could be really helpful instead of just doing random perturbations.
All right, thank you very much, Jason. We'll move on. The next talk is by Randy Chase. The title is Near Real-Time Hail Forecasts Using Machine Learning and Convective Allowing Models. Randy, go ahead with the screen. Yep, looks
Thanks
good.
for that. Thanks for that introduction. Yep, today I'll be talking about hail and doing some near real-time forecasts of hail using machine learning models, and specifically we use UNets. But I wanted to take a moment and say that hail is more than just the U.S. problem. I think a lot of the times, being from the U.S. and being a meteorologist trained in the U.S., we tend to have a U.S. focus. So that's what I'm showing here on the right is the Vivian hailstone from South Dakota. But I'd like to encourage everyone watching that this is also a global phenomenon. Recently, there have been some studies down in Argentina that show hail as a major threat to their life and property and whatnot. So this was conducted as part of the newly formed AI2ES NSF Institute. I have collaborators from across the Institute, including IBM, Central Michigan University, as well as OU and the University of Illinois. This project was mainly done by our two amazing undergraduate students this summer, specifically Jordan and Lydia that you see pictured here. They were part of the OU NWC REU that AI2ES helped fund a handful of students to experience some graduate student-like research projects to get their feet wet in the research field. So like I was saying on the title slide, hail is, hopefully it's pretty evident that hail is quite the damaging phenomena, albeit rare. It does cause quite a bit of problems in the United States specifically too. So it costs billions of dollars to the United States in terms of insurance losses. Things like there's this example hailstone that happened in April 28th of this year, where it punctured through the roof of somebody's house in Texas. And then also a little closer to some of the PIs on this grant, there's a lot of damage in Norman this year, the same day, where these large hailstones damaged a bunch of cars in this dealership lot, as well as Dr. McGovern on this talk also had lots of damage to her personal home in this event. And then lastly, I'd like to motivate it with such instances like solar panels. Earlier today, we had some discussion on PV forecasting from machine learning. So we were kind of interested in, well, what if we could prevent some of these losses? So cars, it might seem apparent if you're a dealership and you have an hour or two of warning, you can then move your most expensive cars to protected regions and or inside possibly. And then maybe solar panels, it might not seem immediately evident, but a lot of these solar panels can tilt. So potentially we could tilt these solar panels into a more protective stance or have them point away from the wind, those type of things to minimize our total loss for these events. So why we have all these numerical weather prediction models out there, and we spend a lot of money predicting and simulating the atmosphere on any given day in the United States. So why are we not getting better at forecasting it? Well, just to keep in mind for those who don't deal with numerical weather prediction on a daily basis, one of our common models called the high resolution rapid refresh, or colloquially known as the HRRR, has a minimum horizontal resolution of 3 kilometers. So I've drawn a theoretical grid box here on the right with a 3 kilometer by 3 kilometer spacing. And so if you imagine, an average hailstone size, if we draw a little magnifying glass here and you could see one tiny little hailstone in there with 1,000 times zoom, you'll see that it's basically impossible to simulate any sort of individual hailstone through a larger thunderstorm. So hail must be parameterized and overall does not coincide well. So these parameterizations result in hails, and some models even don't have a hail parameterization. They actually use Grapple as their main ice category for severe weather. So you could see how this might not coincide with real observed hail size and or location. So that's one of the main problems that we deal with regularly. So kind of as a normal hail forecasting technique, so something like the SPC or National Weather Service forecasters will probably look at identifying regions that are supportive of hail, things that include large buoyancies. So I'm showing some CAPE here from weather.cod.edu, things like SIN, so convective inhibition, as well as wind shear can all give you a potentially supportive environments of hail, and then we issue these potential risks involved. But these are day ahead type of perspectives. We do have some sort of physics-based assessment of how big hailstones will get and where they will fall. This is mainly done through Hailcast, which is a physics model that is kind of run alongside WRF, and I believe it's included more recently in line with WRF. But essentially, you take grid points where convection can occur, and then inside those grid points, we simulate the hail fall that could maybe fall through these updrafts and see how large these stones can get, and that will eventually determine what hail our model is seeing at the ground. And this has been developed for quite a while, but kind of the main limitations here are that it could be computationally expensive to run these simulations. So one way around that is they simulate only five embryos and then take, I believe, the maximum in the standard deviation of those 5 embryos at the end. So this adds time to our computations. So things like the HRRR are very valuable, and you want them to be out on a regular basis, and you don't necessarily want to extend the amount of time it takes to run that model. So that could be one drawback from that. So machine learning has kind of emerged in the recent couple of years as maybe a potential solution that's low cost computationally, at least when you're running it. But training could be computationally expensive and could hopefully fill this gap of forecasting hail alongside the physics-based techniques. So recently, some machine learning methods that have shown promise. I'm highlighting 2 papers from Dr. McGovern's research group in the past. Gagne et al. 2017 showed that machine learning models could outperform Hailcast. That was an older version of Hailcast, but and it also outperformed things such as the updraft helicity and other storm surrogates for the next day hail prediction. And I'm showing one of their figures here on the right. So the top figure is the random forest machine learning approach of predicting hail. And then the bottom is the hailcast. And you'll see that for their data set that they analyzed, the red contours are the observed frequencies, while the blue are the predicted frequencies from the method. And you'll see that the machine learning technique is much more coinciding with the observed frequencies, while hailcast kind of shows this potentially biased result, at least from their data set. Burke et al. In 2020 also showed a similar success story with their machine learning models, and how applying machine learning to the href ensemble could outperform the SPC forecast in predicting the next day hail threat. Even more recently, Gagne et al. In 2019 looked at the next hour forecasts of convective hazards. So I'm showing an example of figure on the right here, the performance diagram, again, where the top right corner is a better skilled model, and the blue line is a logistic regression using the inputs, just mean inputs, while the red is the PCA of the inputs, and then the green here is a convolutional neural network. So what I wanted to highlight from this approach was that they showed that the convolutional neural network, or encoding the spatial pattern of the input variables, was helping this model outperform the more simple gridwise inputs to their method. So in general, this kind of motivated the work of Jordan and Lydia to say, could we potentially do 0 to 1 hour predictions using a convolutional type neural network, and specifically using UNets that have shown a very high skill in segmentation tasks, as well as image to image translation. So that's what we did ultimately. So what I'm picturing here are just some 5 example inputs to our UNet model. Specifically, these are just kind of reflectivities at the lowest kilometer, while SIN is an integrated product, but we have 10 others that are not shown here. And these are 32 pixel by 32 pixel patches. So that corresponds to about a 96 kilometer by 96 kilometer grid. And we have about 49,000 of these input images from her analysis fields that we've collected, thankfully, to the recent archiving of her on Google buckets as well as AWS servers. We then use UNets, that's our main machine learning method. And the outputs that we're actually using, or the labels for this experiment, are the MRMS, maximum expected size of hail. So these are a gridded product that allows us to get around the potential bias of storm reports being only located where population centers are. So each one of the students that worked for us in the summer, one of them did a classification task where they broke it down into no hail, severe hail, and significant severe hail, where the differences are 25 millimeters for severe hail and 50 millimeters for significant severe hail. And then the regression task was done by the other student, where the input images were used to predict the exact MRMS output. So just one other note, the training period was from 2016 through 2019, mainly the summer months based on what we have archived of MRMS. And then 2019, the second half of 2019 and 2020 were used as the test data set. So that was roughly an 85 to 15% split between the groups. So just as a simple example to start out, we start out with that April 28th hail event, kind of a close to home important case study. So you'll see this top panel are the mesh results. The mesh regression, the mesh actual values are found in the A subplots, while the classification results are in the B through D. And then we have stars locating Oklahoma City and Norman, as well as a couple severe hailstorm reports from the SPC storm reports. Then on the second row here, we're showing the actual machine learning outputs. So this first one, again, is the regression task, and then the other 3 are the classification task. And then finally, we compared it to the her hail parameterization. And And you'll see that immediately that the machine learning model tends to capture the spatial extent of this hail event much better than the HERB hail parameterization. Then just some bulk statistics. The pixel by pixel evaluation of the UNet shows pretty good initial results, but just keep in mind that there are a lot of patches that are pixels that have no hail in them. So these AUC parameters might be a bit skewed. And you can see that from this reliability diagram that our machine learning model tends to underpredict the true observed frequency of different events in the testing data set. So I'll wrap up with just some future aspects where we're trying to go with this project. So IBM is a collaborator of our institute, and ultimately we would like to potentially train a model that could be used by the GRAPH model, which is an MPAS 3-kilometer global run. So it might be interesting to run this UNet elsewhere. And it's also encouraging that the UNets performed pretty well without including any of the forecast parameters. So we only looked at analysis. I'd like to acknowledge funding sources, and at this time, I'll take any questions.
Oh, thank you very much, Rocky. Your talk has provoked a lot of side exchanges on Slack. Very interested to note about adaptation to hail, I would say, how to do that, especially in areas where this is really a problem. So we have a question on the Slack, so I'm going to ask that. Do you think ML could be used to supplement, replace certain physical components within a forecasting model, example, hailcast, as opposed to use the output data of a numerical model directly for improved forecasting?
Yeah, I mean, that could be, if we as a meteorological community trust the output of hailcast, yeah, we could potentially simulate, thousands or millions of hailcast profiles and then train a machine learning parameterization of hailcast that could be implemented in a much quicker manner than hailcast itself. So yeah, that could be a viable option, I think. I maybe going one step further, do you think that the model itself, the parameterization in the model itself can be somehow improved? In other words, throwing it back to the model from the machine learning as to how to improve the spatial aspects that cannot be captured by a model like her, and essentially telling it how to maybe improve upon that parameterization. Yeah, that could be, yeah, so just taking the parameterized field and correcting it kind of, so to speak, to the mesh output. That could be one avenue forward. Although I think the way of the future are the P3 type microphysics scheme that allows a mass change of hydrometeor rather than just having discrete mass categories in our hydrometeors to allow it to have a varying degree of rhyming, I think would be helpful in the future.
Okay, and one last question from Slack. Nice to see an example of using the NOAA data sets that are released on the cloud via the big data program. Did you use the data in place on the cloud or egress download to local systems?
So I used I believe his name is Brian Blaylock from the University of Utah. I used his Python package to download the HER data from the cloud onto the OU supercomputer, from which we did most of our processing with the AI2ES GPUs.
All right, I think we have to move on to the next talk. There is one more question, Randy, if you can maybe answer it offline, that'd be great.
Okay, thank you.
All right, the next talk, and forgive me if I'm pronouncing your last name not too well at all, Rocky Talchabhadel, and the talk's titled Spatial Downscaling of Coarse Resolution Satellite-Based Precipitation Estimates to 1 kilometer using machine learning. So Rocky, go ahead.
Thank you. Hello, everybody. I am Rocky, water resource engineer, hydrologist at Texas A&M AgriLife Research at El Paso. Basically, I am learning machine learning and AI recently. So today I'm going to present my preliminary results on spatial downscaling of these coarse resolution satellite-based precipitation estimates to a kilometer using machine learning. Sitish and Saurabh are my collaborator for this piece of ongoing research. Basically, this slide shows the content of my presentation. We are testing our algorithm on a mountainous country, Nepal, Himalaya. We chose this country as developing countries and mountainous countries have a limited number of gauge stations, and most of the hydrologists rely on satellite-based precipitation estimates on those area. So we want to make a scalable approach so that most of the user can use. So we chose regression method to downscale these products. Right now, the method is being tested on daily data, so it's ongoing process. And for the monthly and some seasonal and yearly data, we got some promising results. So I will be presenting a few of the results. Before that, as we all know that precipitation is one of the crucial components of any hydrologic and water balance analysis, but they have higher spatiotemporal heterogeneity, so they cannot directly be forced into hydrologic model because of its coarse resolution. Traditionally, to solve the spatial distribution, we rely on interpolation technique with gauge observation, but as we all know, interpolation is dependent on number of stations, and as I already mentioned, these stations are very much sparse in mountainous countries. And recently, as we all know, these satellite-based observations are advancing a lot, and it is being same applied for precipitation estimates. And we need to know that these satellite-based precipitations, even they are at coarse resolution, we can predict them with other variables which are available at high resolution. So we are testing these with at first with simple available data that are dependent on location, topography, and other basic indices. But we plan to make this scalable model available to users so that they can plug in and plug out with the available data. And we plan to make the model in Google Earth Engine using random forest, so that that would be easy for lots of people to use on their locality, on their region. Here, Nepal, we chose a study area. Before going to topic, I would like to highlight the spatial distribution of precipitation in a mountainous country is too high. As you can see, these blue pockets are having almost more than 5,000 mm precipitation in a year, and exactly just maybe just few kilometer northern side of that area, it has only like less than 200 mm precipitation due to the orographic effect of mountainous topography. So this kind of orographic has a higher effect on precipitation, and we try to predict this precipitation using topographic information, that is latitude, longitude, elevation. And as I already mentioned, the orographic effect, we try to incorporate using aspect. And another thing is, even on temporal scale, the total annual precipitation, they just are concentrated on few months, like during monsoon, 4 months, almost 80% of annual precipitation occur at every location. And again, if we look on winter precipitation, it's just 3% of annual precipitation. So this is the, I think, overall characteristic of southern monsoon in Southern Asian countries. Here we try to take the advantage of Google Earth Engine, and right now we are using data available in Google Earth Engine platform, and we try to use Predict10 also using Google Earth Engine. Here we are taking 4 satellite precipitation estimates that are ships in 5 km resolution, IMERS, that is final version on 10 km resolution, and 2 coarse resolution precipitation. They are based on TRIM and Persian. Here we try to make a model on a firstly on a coarse scale resolution. So those all predictors are just converted into coarse resolution. For chips, it's 5 kilometer, and for IMER is 10 kilometer. And based on the predicted machine learning model, we again force them with the 1 kilometer resolution data so that we can have the final result of downscaled satellite-based precipitation estimates. We are trying to use other different machine learning model also, so that for that we are using Google Colab, and we plan in future to select the best model. And if random forest works properly, then we would just provide a goal of engine based model based on random forest. Here on experimental level, I am presenting a few results from a simple method, that is multiple linear regression, and for the machine learning, we chose random forest. And as I mentioned, when we chose latitude, longitude, and elevation as only predictor, then it's location only, and we added slope and aspect, and we allow other to add other parameter as well. For now, taking MODIS land surface temperature as one of the predictor. It might be difficult, like temperature is spatially varying in a smooth way, but precipitation has localized concentration on heterogeneity. But we are trying to experiment these models, and when we would be having some good model, then we would be finally testing. And for the testing, we are using popular indices, that is for detection, POD, CSI, FAR, and for magnitude, we are comparing the deviations in terms of mean deviation and absolute deviation and RMSE. Before moving to the downscale data, firstly, I would like to show the performance of the raw data. Here, these top three are related to detection indices, and we clearly see that CHIRPS in terms of POD is too low. That means CHIRPS is not performing that much to on a daily scale. But if we compare on magnitude side, all these SPEs are showing similar results, except the Persian one, which is having slightly underestimated result. And to solve the underestimation of this parameter, we are trying to blend this product using another machine learning. That is also ongoing process. And we have a poster the day after tomorrow on the blending part. Here, I would not go on that thing. And if we see on some of the popular rainfall indices, as we can see, these satellite-based precipitation estimates are not even good enough to capture the variability on a gauge location for mountainous country. So these might be limitation. If we just downscale the product, we are not solving this problem at all. Here, these dots are the gauge data from 231 stations. Right now, I'm just showing a sample of 2015. As you can see, the spatial distribution of chips is somewhat matching with observed spatial distribution, but on a daily scale, when we look on the probability of detection, it was not good enough on detection scale. So there are lots of limitation on those satellite-based precipitation estimates. And when we try to downscale this product, if this picture shows the downscale image using multiple linear regression. So it had almost similar result with the raw data, because we downscale the data, taking their data as a source, and but we did not solve the problem related to detection and that magnitude part, which is still ongoing. And in terms of random forest also, here I just tried to show one sample for trim data. We tried to use Google Earth Engine here with those data set and downscale. What we find quickly was, like, for the random forest, we found the elevation was the most important model feature. and we are testing with other parameters, and we are trying to come up with the final version of model. So it's a preliminary result. We haven't got the final model at all. And just to let you know, we have tried to scale the model tested on Nepal. We tried to use on a bigger scale, that is a Hindu Kush Himalaya, that covers a few other countries adjacent to Nepal. And what we found was like on an average scale, the location where they have like average precipitation, they were quite matching on a downscale location on pixel basis. But the location where the precipitation is quite extreme, for example, here I showed in red pocket, those extreme are underestimated on downscale pattern. So we are still trying to figure out to solve the extreme part of the precipitation. The result is similar for seasonal and monthly, but on a daily scale, we are using the model, and it has not yet completed. So after the model has been run with daily data for all those 4 selected SPEs, we shall be checking the performance. So that's ongoing, and our future plan is to bias correct these SPEs and blend these SPEs with gauge data, and finally downscale the daily data. So the presentation that I made is a part of this ongoing project, and we have a poster presentation the day after tomorrow on the selection of different machine learning algorithm to blend these satellite precipitation again to better estimate at each location. That's all from my side for this presentation.
Thank you very much, Rocky. That was a very nice presentation, and trying to solve a problem in a very difficult area, given the orography problems that exist in the domain. Let me wait for a second to see if there are questions on Slack. Okay, I have one question, which is your final slide says talks about correcting biases in the SPEs. I noticed that chirps, which is which seems to be the most highly resolved in terms of spatial dimension, was not giving you result diurnal base, right? On the daily scale, diurnal scale. Why? I mean, you would think that having the highest spatial resolution, it probably should be doing better than the others. Is there a sort of a counter argument to that? Why that particular thing is actually not the best?
In terms of spatial resolution, CHIPS has got the best spatial resolution, 5 kilometers. But what happened is on a daily scale, it is not performing to that level, because the CHIPS data are solved with the pentad data as a gauge correction in itself. So what happened is on a 5-day level, they have some sort of gauge correction on their algorithm. So when we look at monthly data, annual data, CHIPS perform to good extent. But when we look on daily extent, so the rainfall detection that is showing by gauge data might not shown by CHIPS. So there is like conflict between CHIPS and gauge data on a daily scale. But when we look at just amount in terms of deviation, it's again, if you compare on a monthly and seasonal scale, CHIPS outperform other data. But when we look at daily to daily data, for example, if you look on RMSE error, it shows higher results, higher values. But if you look at just mean error, which is compensating 1 plus positive error with negative error, it has like somewhat good results. So in terms of mean error, it shows good result. But in terms of mean absolute error, it has a higher deviation because of day-to-day deviation, I guess.
Okay, well, thank you so much. And I think we'll have to move on. And we now come to the final talk of the session, and yet another different topic. So it's been an array of varied topics in the session. And the last talk in the session is by Linsey Passarella. I hope I'm pronouncing the last name correctly.
Yes.
The title is Using Multitask Learning to Isolate the Response of Western US Precipitation During ENSO Events. So go ahead, Linsey.
So can everyone see my screen?
Yes.
Okay. Yeah, so my name is Linsey Passarella. I'm a graduate student at the University of Tennessee. And part of this work was done at Oak Ridge National Lab. So what I want to talk to you guys today about is I use a multitask autoencoder to kind of maximize the ENSO, the response of Southern California precipitation with ENSO. And so, traditionally we use indices such as the Nino 3.4 index, the Nino 3, the Nino 4, the Nino 1, the Nino 2 to identify these ENSO, these El Nino and La Nina events. We also use things such as a principal component analysis, where the first PC is your strong ENSO event, and the second PC could be your weaker ENSO event, such as ENSO Modoki or the Central Pacific El Nino. But there have been some issues with using this linear model or linear models like the PCA. The strict bi-orthogonality of the components make them difficult to interpret, and they don't also necessarily relate to a physical phenomenon. Some studies have even shown that they're not orthogonal to begin with. And so we want to explore these kind of nonlinear ENSO indices. And one way we can do that is through explainable machine learning. And so we can identify these nonlinear patterns of tropical sea surface temperatures. I know that there is, and we'll look at it and talk about it a little bit later. The ENSO longitude index is currently a nonlinear index used to define ENSO events. And again, I'll mention that later. But back in 2016, a researcher found that an autoencoder was an effective way of reducing dimensions in data set and detecting repetitive patterns over other techniques like the principal component analysis. So where the principal component analysis is mapping your data onto a lower dimensional hyperplane, the autoencoder can map it to a nonlinear latent space if you're using a nonlinear activation function. And so we kind of build upon that. And so we say, okay, could we use a multi-input and multi-output autoencoder if we want to look at two variables that are present? So here we construct a multi-input, multi-output autoencoder where we train it on sea surface temperature anomalies over the tropical Pacific and Southern California precipitation. And so we can effectively extract the most prominent features between those two variables. So what we're trying to do is kind of create this ENSO index that's nonlinear in nature, but that's also maximizing the influence of an important teleconnection, which is Southern California precipitation. And we know from previous studies that this Southern California precipitation is highly correlated to the to ENSO events, but traditional indices like the Nino 3.4 have had some issues in the past with determining like a high Nino 3.4 index might not mean that we'll have high precipitation in Southern California that year. For example, the 2015-2016 ENSO event was forecasted to have a high Nino 3.4 index. And so all the models predicted that it would show above average precipitation like previous ENSO events. However, they didn't see that in the 2015-2016 year. So we want to look at if we can maximize that response while capturing the linear variability. So I want to start out with just what is a simple autoencoder. So an autoencoder is, it wants to learn an identity function. So your input and your outputs are going to be exactly the same. And the autoencoder wants to learn how to efficiently compress the data into this hidden layer so that your reconstruction, so you're maximizing reconstruction. So in that way, if you have two nodes in your hidden layer, you can kind of think of it as that projection onto a latent space, so such as like the PC1 and PC2. I do want to point out that studies have also shown that using a linear activation function in a simple autoencoder like this with two hidden layers is very similar to doing a principal component analysis, and those two hidden layer nodes become like a PC1 and PC2. So we want to extend this general architecture to include multi-inputs and multi-outputs. So here you can see that we've kind of focused in on Southern California. So this is our precipitation data. We flatten it. It goes through 50 node hidden layer, 10 node hidden layer, and then it bottlenecks into this single node hidden layer in which it's concatenated with our tropical Pacific sea surface temperature anomalies. And so we're trying to, in this single hidden layer node, create an indice that has maximum shared variability between both California precipitation and tropical sea surface temperature anomalies. And so here we're looking at the R² value of different nonlinear activation functions. And what we want to do is we want to pick the activation function that is most highly correlated with other known indices. So here we're looking at the Nino 3.4, PC1, PC2. We also include ELI, that nonlinear index that I mentioned earlier, the ENSO longitude index, and then also the general precipitation anomalies in this area. So we found that using a TNH activation function was best for maximizing similarities between our known indices and also precipitation. So here we take, once we train our autoencoder, we train it on, I forgot to include that slide. We train it on historical model data. And so we use I think it's 165-year run of historical model data. And then once we've trained that, we run it through observational data. And our trained hidden layer weights become our new index. So what we do is we regress that index onto our sea surface temperature pattern in our observational data and our US precipitation pattern. And so we can see that our our multi-input, multi-output autoencoder, and I'll call it MIMO-AE from now on, it picks up the correct sea surface temperature pattern that we expect to see. We note that it is a little, it's less strong than the Nino 3.4 pattern, but we kind of expect that because we're also wanting to maximize the variability between precipitation. And here with our precipitation patterns, you can see that our MIMO-AE is highly correlated to precipitation patterns in Southern California, as well as some places, you know, expanding from that. And when compared to the Nino 3.4 index, it's picking up this, this pattern much more. Then we also want to look at our top 10, what our MIMO-AE categorized as our top 10 strong El Nino events, and what the Nino 3.4 categorized as the top 10 strong events. And we're looking at just the average composite analysis of average precipitation per day. And so we can see that our MIMO-AE is more highly correlated with precipitation events in the Western United States. And as well, it's picking up a little bit in the Southeast as well. And when we compare that to the Nino 3.4 index, we see a similar response, but just not as strong. We also see a stronger response to La Nina. So we do know that the Western, we kind of see an opposite effect during La Nina. And we do know that that effect on precipitation in the United States is asymmetrical for La Nina and El Nino. So we expect a weaker response here, and we can kind of see that as well. And then this is a lot, but we'll go through each one of these. So in the top row, we want to look at the peak sea surface temperature anomalies along the equator and their corresponding longitude. So here we have longitude, and here we have our peak sea surface temperature anomalies for both the Nino 3.4 and the MIMO-AE. So we see for both of these indices, you know, we generally see weaker events happening in the Western Pacific, with our stronger events happening in the Eastern Pacific, which we expected to see. We also can see that our MIMO-AE captures a greater spatial distribution of events. And so generally these events that are happening between like 160 and 200 degrees longitude are those Central Pacific or ENSO Modoki events that are happening. And we can see that it's picking up those events better than the Nino 3.4. That also makes sense because the Nino 3.4 is confined to a specific spatial area when you're computing that index. So that's generally something that we would expect to see. So then we want to look at, and specifically we want to look at our 2015-2016 El Nino events to see what our MIMO-AE categorized it compared to the Nino 3.4, because we know that the Nino 3.4 categorizes it as a high event, but we don't see the same precipitation response. So here we can see for 2016, our MIMO-AE categorized it as like a mid-level response where it's the highest in our Nino 3.4. And similar, this is for June, July, August, and this is for December, January, February. So we can see that both in winter and in our summer phases of ENSO, we're seeing a similar response. I also want to note that you can see that like for our MIMO-AE, 2005 was the highest year. And again, it's over here. And I want to note that those were events that saw roughly 200% above average precipitation in Southern California. And so that it doesn't necessarily correspond to an ENSO event. It is associated with an ENSO Modoki event, but also just California saw a lot of precipitation. So we could take that as a suggestion that, okay, maybe our MIMO-AE is putting a lot more input into the precipitation than we'd like. And then we have our last graph here, which we just want to look at the nonlinearity of our MIMO-AE compared to like similar nonlinear indices such as the ELI. And so we can see that it shows this similar pattern compared to the Nino 3.4, which is more normal in distribution. And so we expect to see a little bit of skewness where we have fewer high ENSO events, a lot of neutral ENSO events, and not as many La Nina events. And so I think I'm running out of time, but that's all I have. So if there are any questions, yeah.
Thank you very much, Linsey, for an interesting talk, particularly because the El Nino of 2015-2016 was so unusual in terms of the precipitation over Southern California. We have a question on the Slack. Why was one node chosen as a bottleneck in the autoencoder? Were experiments conducted using different sized bottlenecks?
Yeah, so I did conduct a bunch of different sized bottlenecks and then compared each node to this Nino 3.4, PC1, PC2, ELI. And what I found was that if I compress the data by itself and then send it to a single bottleneck, it picks up maximum variability. I looked at one where I used like 10 nodes in this bottleneck layer, or I would use 10 and go to 1. And I just found through all my playing around that 1 was the best, and it didn't make a huge difference if there were more than 1, because 1 would still pick up the maximum. 1 node would pick up the maximum variability, and the rest would kind of have weaker variability in it.
So I have one quick question, and feel free to answer it very short because we're running out of time. But you mentioned the reason you sort of saw that the Southern California precipitation was not correlated with the Nino 3.4 for the 2015-2016 El Nino event. Did you try applying the new technique to the 97-98 El Nino, where actually there was a correlation between 3.4, Nino 3.4 and the Southern California precipitation?
Yeah, so here's the 97 event.
Ah, okay.
So it is showing a higher MIMO-AE.
Yeah.
But again, like I said earlier, this 2005 event, and I think it was it 1992? There was another event where Southern California just saw a ton of rain, and that kind of skewed it a bit. But
okay.
Yeah.
Very nice. So thank you so much for your presentation. And I want to thank each and every speaker in the session. what an exciting array of topics presented, every one of them different and every one of them indicating the really rapid growth of machine learning into the environmental sciences field on every facet, atmosphere, severe weather, oceans, coupled atmosphere-ocean interactions. So thank you so much, everyone. And I would now, with your permission, would like to close the session. And again, feel free to drop your comments or questions in the Slack. I think the speakers can pick it up later on and respond to them. So with that, I'm going to turn it over to the organizers. Susan, can I turn it over to you?
Sure, I don't have anything further. I'm not sure if
We need to end the recording.
I can. It ends by itself. That's not a problem. But I encourage everybody to go over to the poster session and visit all the posters that are there. There's a subset that will have live video chats, and have a great rest of your day.
Okay. Thank you so much, everyone.
Thanks, you guys. Thanks.